So in this lesson, we're going to cover probability tables, probably a very common type of question we'll see. They're actually helpful to make our own in certain scenarios. So we'll first take a look at this one. I'm going to read through the question. A local company is interested in supporting environmentally friendly initiatives such as carpooling among employees. The company surveyed all of the 200 employees, and so that's represented down here in the bottom right corner. Employees at the downtown offices. Employees responded as to whether or not they own a car and to the location of the home where they live. The results are shown in the table. What is the probability that an employee owns a car? So this is not a conditional probability. This is just referring to the total number of people. So the people that own a car is going to be this yes row, and there are 60 out of 200. What is the probability that an employee lives outside the city? All right, so we're looking at the outside the city area, and so that's this column. Again, it's the total of that column out of the total number of employees. So that's also 60 out of 200 for a different reason, but 60 out of 200. And again, I could reduce these. I could call it 3/10, but leaving them in their non-reduced form kind of brings more meaning to where these numbers come from. Okay, so letter C here, what is the probability that a person does not own a car and lives in the downtown area in the city? So this is what we call a joint probability, the probability of two things occurring at the same time. So that information comes from this portion of the table. So the probability that they do not own a car, so that's this row, and downtown area in the city is this column. And so the overlapped region is that number, which again, coincidentally is 60 out of 200. All right, part D. What is the probability that a person owns a car or lives elsewhere in the city? So this one we have to be a little bit careful with. These are not mutually exclusive events. So we would have to be mindful of double counting. So if we look at the probability that a person owns a car, that's going to be the top row. And maybe I'll even use a highlighter here. So we have the top row. Those are the people that own a car. So there's 60 total people that own a car or live elsewhere in the city. So that's going to be the middle column here. And so some people make this mistake when they answer this question and say that the answer is going to be 60 plus 70, which is 130 out of 200. Now, if we did that, you could see that when I did my highlighting here, if I add 60 and 70 together, I just counted that 15 twice. So we have to subtract away 15 out of 200, which would give me 115 out of 200. Now, this is reminiscent of the formula we talked about where the probability of event A or B is equal to the probability of event A, which in this case we're letting A represent the elsewhere in the city, plus the probability of event B, which is the own a car, or vice versa, whatever. So that's where the 130 out of 200 comes from. But again, we have to be mindful of the fact that we just double counted. So the A and the B are represented in that. I added those together. And then the 15 out of 200 is the overlap or the intersection. Another way you could actually answer this question is by, instead of using the margins, and the margins being the 60 and the 70, if you go ahead and just add these numbers together, it's a little bit more math, but it kind of avoids the double counting. So if I do 10 plus 15 plus 35 plus 55, that also gives me 115 out of 200. All right, so this last one here is given that a person lives outside the city. So now we're talking about a conditional probability. And so given that a person lives outside the city, that's our condition. in probability notation, I could write that as the probability of something, where we haven't figured out what something is. And I'm going to use the letter O for outside the city. And what is the probability they own a car? So in the top, that's a yes/no question. So we'll put yes, they own a car. All right, so really the condition limits us and says, okay, given that they live outside the city, we're limiting ourselves. So I'm going to erase all this stuff that I've got on the table here. We're limiting ourselves to this column. And we're saying of those 60 people, so that's our condition, 60, how many of them own a car? So that's 35 out of the 60. So why don't we practice another one of those? Okay. A nice contentious table representing politics. Okay, a survey of 1,005 US adults, so that's the total. What is the probability that the person thought Trump best fits their presidential ideal? And so no conditions, no ands, no ors. So we're just looking at 518 out of 1,005. What is the probability that the person is younger than 50 years old? So that's essentially going to be these two age groups added together. So that's going to be 217 plus 416 out of 1,005, which is 633 out of 1,005. Now, those two events I didn't have to subtract any overlap because they're in two separate columns. They are mutually exclusive. A person can't be in the 18 to 29 range and the 30 to 49 range at the same time. What is the probability that the person is younger than 50 and thinks Clinton best fits their ideal? So younger than 50. So that's going to, again, be these two columns that we pointed to before. And thinks Clinton fits their best ideal. Well, that's those two added together. And these are not conditional probabilities. So it's going to be 135 plus 158 out of 1,005. So that's going to equal 293 out of 1,005. What is the probability that a person is younger than 50 or thinks Clinton best fits their ideal? So the younger than 50 group we have is 633. The Clinton group is 437, so that's the margin value there. So again, if I add these two together, I'm going to have an issue because I just double counted the 293 people that fit both categories. So I have to subtract away 293. And again, this is all out of 1,005. So when we do that, we get 777 out of 1,005. All right, so now we're getting into these conditional. So anytime you see given, that's a key, that's a dead giveaway that this is a conditional probability. So the condition for this one is given that the person picked Clinton. So that's our condition. So that's our denominator. All right, so our denominator is how many people picked Clinton. And again, that's 437. So of those 437, what is the probability that the person is 18 to 29? So now that's going to be this value over here out of 437. So 135. All right, another conditional probability where we just reverse the order. So this time we rewrote it so that the condition is the 18 to 29 category. So that's our condition. So now I have to look at the 18 to 29 column, which is 217. All right, so that's our denominator there. And the numerator is still 135. If the person picked Trump, what is the probability that they are over 65? So this time it doesn't say given, but it's kind of saying, all right, if the person picked Trump, that's our condition. All right, we're limiting ourselves to that category. All right, so now we're going to go back and look at how many people picked Trump, and that'd be 518 as our denominator. So our condition gives us a denominator of 518. What is the probability that they are over 65? And of the 518, that would be 92 out of the 518. All right, so that covers these few pages. I'm going to put out another video just to talk about conditional probability a little bit more because it can be kind of tricky and it can be misleading in terms of information. And it is kind of a way you could trick somebody into believing something that may or may not be true. So I'm going to put that out as a separate video because this one's getting a little long. All right.